So how do we use this result? Let's say we have a sequence that is defined inductively or recursively by giving the first term, a1 is 1, and giving a rule for each n to go from one term to the next, in this case, namely that a indexed by n plus 1 is 3 minus 1 over an. And we want to know if it's convergent, and if it is, we want to find the limit. So how to proceed for that? Well, we're going to start by looking at the first few terms. So a1, the first term, is given to us, it's 1. To calculate the second term, I have to use my induction formula. So a2 is 3 minus 1 over a1, that's applying the formula in the case where n is 1. Since a1 is 1, that's 3 minus 1, 2. So a2 is 2. To find a3, I'm going to use the induction formula again. I use it when n is 2. I get that a3 is 3 minus 1 over a2, but I found a2 to be 2, so I get 3 minus 1 half, 2.5. a4 is 3 minus 1 over a3, and I found a3 to be 2.5, so we get 2.6. a5 is 3 minus 1 over a4, and I found a4 to be 2.6. We plug things in, we get approximately 2.615. Okay, that gives us an idea of the behavior, at least at the beginning. And from this we could guess that maybe this sequence is non-decreasing. This is what it looks like, at least from the beginning. And also that it is bounded. Well, it looks like it should be bounded by 3 because it's 3 minus 1 over an, and it looks like the an's are non-negative. So how to prove this kind of properties? Because checking it on the first few terms is certainly not enough to conclude that the sequence indeed does have this kind of properties, which are properties to be verified for all n. So how do you prove properties for all natural number n? That would mean checking for infinitely many values of n. That's not something we can do. So a basic proof technique for these type of things is to prove this by induction. So to prove a property p of n that depends on a natural number n, to prove it for all natural number n, you would prove it at the beginning, prove that the property is true when n is 1, and then prove that if it is true for a certain n, it is true for the next. In other words, for all n, you want to show that if p of n is true, then p of n plus 1 is true. Because if we prove that we have that p of 1 is true. And we have that if it's true for a certain n, it's true for the next. So if p of 1 is true, then p of 2 is true. But if p of 2 is true, then p of 3 is true. If p of 3 is true, then p of 4 is true. And so on. And so you have this domino effect which shows the property for all n. So that gives us 2 steps to prove in order to prove that the property is true for all natural numbers, so for infinitely many. So can we do that to prove that the sequence is non-decreasing? Well, we need to specify the property p of n that we want to prove by induction. And so this p of n in this case would be that a indexed by n plus 1 is greater or equal to an. If we can prove that for all n, then we would have proved that the sequence is non-decreasing. So if we are going to proceed by induction, we first need to verify that p of 1 is true. In other words, when n is 1, that we have a true inequality. And this is easily checked because a2 is 2, which is greater or equal to a1, which is 1. So p of 1 is true, and now we need to prove that if p of n is true, then p of n plus 1 is true. We know p of n. P of n plus 1 is what we obtain by replacing n by n plus 1 in the property. So we get a indexed by n plus 2 greater or equal to a n plus 1. So what we need to show is that if an plus 1 is greater or equal to an, then an plus 2 is greater or equal to an plus 1. So how are we going to do that? Well, we have a formula that tells us how to obtain a term in terms of the preceding one, an plus 1 in terms of an. So this is what we're going to use. We start from a relationship between an plus 1 and an, and we want a similar relationship for the next n. But the way to go to the next n is to use this formula that gives us an plus 1 in terms of an. Abstractly, we have an plus 1 as a function of an, and so we're going to apply this function to our equality, because if I have an plus 1 is f of an for all n, then f of an plus 1 is going to be an plus 2, f of an is going to be an plus 1. So we apply this function f, which is in this case 3 minus 1 over x. Right, because an plus 1 is 3 minus 1 over an. So how do we do that? Well, I start with an plus 1 greater or equal to an, and I follow the steps to go from one term to the next. So what do? We take 1 over an, so we take the reciprocal, then we multiply by negative 1, then we add 3. And that will build 3 minus 1 over an. So we do that on both sides of the inequality. When I take the reciprocals, it reverses the inequality, so I get 1 over an greater or equal to 1 over an plus 1. When I multiply by negative 1, it reverses again the direction of the inequality, and I get negative 1 over an plus 1 greater or equal to negative 1 over an. When I add 3 on both sides, I preserve the direction of the inequality. And now, because this is the formula that gives me one term in terms of the preceding one, what you have on the left-hand side of the inequality at the bottom, 3 minus 1 over an plus 1, is an plus 2. It's just applying this formula that we have at the top for n plus 1 instead of n. And what we have on the right-hand side of the inequality, 3 minus 1 over an, is an plus 1. In other words, this inequality is simply an plus 2 greater or equal to an plus 1. So what we have proved here is that if an plus 1 is greater or equal to an, then an plus 2 is greater or equal to an plus 1. In other words, Pn implies Pn plus 1. And since we've already checked that the property Pn was true for n equal 1, we have proved by induction that our sequence is non-decreasing. So now, is it bounded above? Right, because we have it non-decreasing. If we can show that it's bounded above, then it's non-decreasing and bounded above, it has to be convergent. Well, a natural candidate for an upper bound is 3, as we pointed out before, and so we can try to prove that again by induction. The property Pn that we want to show for all n is now that an is less than or equal to 3. If we show that for all n, then 3 is going to be an upper bound. So we start with P of 1, and this is easy to check. A1 is 1, that's certainly less than or equal to 3, so P of 1 is true. Then we turn to, if we have P of n, then we have P of n plus 1. In other words, we want to show that if an is less than or equal to 3, so is an plus 1. Again, we're going to focus on the relationship that gives me one term of the sequence in terms of the preceding one. And I'm going to start with an less than or equal to 3, and then follow the steps to go to the next term in the sequence. In other words, I'm going to take the reciprocal, multiply by negative 1, and add 3, which are the steps to go from an to an plus 1. So if an is less than or equal to 3, when I take the reciprocals, I reverse the direction of the inequality, and 1/3 is less than or equal to 1 over an. When I multiply by negative 1, I reverse the direction of the inequality again, and I get negative 1 over an less than or equal to negative 1/3. Adding 3 on both sides preserves the direction of the inequality, so I get 3 minus 1 over an is less than or equal to 3 minus 1/3, which is of course less than or equal to 3. But 3 minus 1 over an is really an plus 1, so I have obtained an plus 1 is less than or equal to 3. So I have proved the second point in my proof by induction, and the conclusion is that the sequence is not only non-decreasing but also bounded above, specifically bounded above by 3. According to the result that we have proved before, the conclusion is that the sequence is convergent. So now the problem is to find the limit. How do we find the limit? Well, we're in the case where an plus 1 is obtained as a function of an. So we have an plus 1 is f of an. Something that we have observed in one of the previous videos, one of the basic properties of sequences, is that if we have a convergent sequence, then a continuous function is going to preserve the limits. In other words, if I form a new sequence by taking the image of each term under the continuous function, I obtain a new sequence, f of an, and this is going to have to be convergent as well, and the limit is just the image of the limit. This is something that we have pointed out before, and now we're in the case where an plus 1 is f of an, where f is 3 minus 1 over x, which is a continuous function except at 0, but we have proved that the sequence which has first term 1 is non-decreasing, therefore we stay away from 0. So that means that the limit of an plus 1, which is the limit of f of an, has to be f of L, whatever this limit L is, but we know that this limit L exists. But the limit of an plus 1 is really what is the value approached by a indexed by n plus 1 as n goes to infinity. This is of course the same as the limit of an. Shifting the index by 1 is not going to change the behavior at infinity. So we end up with L equal f of L as a necessary condition for the limit. So what we have proved here is that if we have a convergent sequence that is defined recursively by an plus 1 equal f of an, where the function f is continuous, then the limit L of the sequence is necessarily a fixed point for the continuous function f. Fixed point in the sense that L equal f of L. So we're going to use that to find our limit. In this case, f of L equal L, where the function f is 3 minus 1 over x. This equation writes as 3 minus 1 over L equal L. Multiplying both sides by L, we obtain 3L minus 1 equal L squared, which is a quadratic equation in L that can be rewritten L squared minus 3L plus 1 equals 0. And applying the quadratic formula, we find that L is either 3 plus root 5 over 2 or 3 minus root 5 over 2. So which one is it? Well, 3 minus root 5 over 2 is less than 1, because root 5 is more than 2. And so it cannot be the limit, because our sequence starts at 1 with a1 equal 1, and then it's non-decreasing. So certainly it cannot approach a value less than 1. And that leaves us only one choice, which is that the limit of the function, which we know exists, has to be 3 plus root 5 over 2. So now turn to the next video where we're going to consider other such examples.